All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. This is for HL Chemistry, and we're continuing through as we're talking about topic number 2, which focuses on atomic structure. And in the last video, we dived into all of the different models of the atom leading up to our quantum mechanical model, which is our current model, which we use for our understanding of the atom. Now, as we're looking through this, we're going through and reminding ourselves of some important pieces of information that are helpful for us in the context of chemistry and communicating about the atom in terms of isotopes, protons, neutrons, and electrons. And so today, in this particular video, we're going to be looking at what do the nuclear symbols of our elements, how can they help us determine the number of protons, neutrons, and electrons present in an atom or an ion. You could probably even throw in there the term isotope as well. So in an isotope or an ion, how can that nuclear symbol help us figure out the number of protons, neutrons, and electrons present? Pretty basic skill, but it's something that we have to come back to, make sure that we're all on the same page. So let's go ahead and dive right in, ladies and gentlemen. So we know that the atomic number is the number of protons in the nucleus. If you remember, Henry Moseley is the person who's responsible for kind of coming up with this term. It's the number of protons in the nucleus, and when you look at your periodic table, that's the whole number that is present in the element symbol box on the periodic table. All right, your mass number. Now, we always have to remember this is the number of protons plus the number of neutrons in an atom. Now, the mass number cannot be found on the periodic table. That would be something that has to be provided to you, or other information has to be given so that you can find it. But again, it's simply the number of protons plus the number of neutrons in an atom. And the last thing here, isotopes. We know that different atoms have different isotopes. They occur with different numbers of neutrons in their nucleus in nature. And so when we look at that, an isotope is simply an atom that has the same number of protons, but a different number of neutrons. And you can also think of that in terms of different mass numbers as well, right? Like carbon-12 versus carbon-13 versus carbon-14. They're all carbon because they have 6 protons. The thing that's changing, the number of neutrons in the nucleus, which ultimately changes the mass number of our atom. Now, again, this should be a notation that we're very familiar with. And so you've got your generic element symbol X. Then you've got that superscript A, which is your mass number, which we've just talked about. It's the protons plus the neutrons. And then you've got the subscript Z, which is your atomic number. That's going to tell you the number of protons present within your atom. And certainly this is a notation that you should be familiar with, and from a nuclear chemistry perspective, that's a notation that is very common so that you can quickly identify mass number and atomic number so that you can use that information to determine protons, neutrons, and electrons within a given atom. Now, ions. We know that ions are atoms that have either lost or gained an electron from their valence shell, typically. And those ions can come in 2 different forms. You can have a cation, which is a positive ion that's formed by the loss of 1 or more electrons. Certainly, if you recall, those are typically going to be your elements that are metals on the periodic table. But if you start looking at it from the perspective of periodic trends, your cations are going to be your substances that tend to have relatively low ionization energies. They have weaker Coulombic forces of attraction with their valence electrons, and therefore it's easier for them to lose electrons in that process. Whereas your anions, those are going to be negative ions that are formed by the gaining of 1 or more electrons. Again, those tend to be your nonmetals on the periodic table. But again, if you think about it from a periodic trends perspective, your anions tend to be elements that are very small in terms of their size. They're generally very electronegative, so in bonds they tend to attract electrons to themselves, and they have relatively high ionization energy. So all of these things kind of contribute to the fact that anions gain electrons and the atom becomes negative because the number of electrons is outnumbering the number of protons. All right, so with that shorthand notation, if you look at that symbol where the mass number and the atomic number are given, the isotopic information for an ion, you should be able to figure out how many protons, neutrons, and electrons are present based on the information that's given there. And I believe that should say the atomic number. So remember, the atomic number identifies the element. And you could think of it as that's the number of protons that identifies the element itself. If we're dealing with something that is electrically neutral, if it doesn't have a charge, we know that essentially the atomic number and the number of electrons are going to be equal then. And then if you have an ion, you just got to keep in mind if it's a positive ion, that means that your protons are going to outnumber your electrons. Or if it's an anion, your electrons are going to outnumber your protons. All right, now again, that's just going to be depending on whether or not you have a cation or an anion. Just going to keep that in mind as you're looking through those things. Now, looking at isotope symbols, right? So we know something like chlorine, for example, exists as two isotopes, chlorine 35 and chlorine 37. So there we go. We have our symbol there. We've got the mass numbers that are in the upper left corner. Notice in both of these, they've left off the atomic number, but for chlorine, that's atomic number 17. Now, you can also write those two isotope symbols using what's called dash notation, where you write the name of the atom and then its mass number after it. So, for example, you could write that chlorine 35 and chlorine 37. And again, once you started to get into it, if you started to break down how many protons, neutrons, and electrons each of those isotopes had, the difference you would see between chlorine 35 and chlorine 37 would be the number of neutrons that are in the nucleus, right? So in our chlorine 35, it's going to have 17 protons, 17 electrons, but then it's going to have 18 neutrons. But in chlorine 37, you're going to have 17 protons, 17 electrons, and then 20 neutrons, right? So again, the difference between those two isotopes, the number of neutrons, chemically, they behave the same exact way because they have the same number of electrons. Because remember, electrons determine chemical properties, protons and neutrons determine nuclear reactions and things like that. All right, some other examples to consider. So again, we've got our chlorine 35, 17 protons, 17 electrons, and 18 neutrons. If you had the aluminum 3+ ion, now we're assuming that this is aluminum 27 then. They didn't give the mass number here. But aluminum 3+ has 13 protons, 10 electrons, and 14 neutrons because we're specifically dealing with the aluminum 27 ion/isotope of aluminum. All right, then here we've got fluoride 19. So you've got 9 protons, 10 electrons, and 10 neutrons. We have 10 electrons here because it's a fluoride anion. It's gained 1 additional electron. And so the number of electrons need to outnumber the number of protons. All right. Now the last thing we're going to be taking a look at is we should be able to determine the relative masses and charges of the subatomic particles. That should be known to us. And even in your previous classes, we've talked about how the mass of the electron can be considered negligible. And so you've probably seen a chart like this very similar before. I'm confident I've shared something like this in honors chemistry and certainly in AP chemistry as well. But you've got the different particles. You've got your proton, your electron, and your neutron. And then you've got the relative mass and relative charge of both of those, or all 3 of those subatomic particles. And if you notice, for the proton and the neutron, they've been given a relative mass of 1. Now again, they came up with that relative mass because they wanted to put the mass of the proton and neutron and electron in perspective and give you something that was a little bit more tangible than the really small mass that the proton, neutron, and electron have. And so that number 1 is just what we give to it so that we can kind of conceptualize it to give it so we can work with it, right? And then the proton has a +1 charge. Now you see our electron has a relative mass of 0.0005. That's why we can say that the relative mass of the electron is negligible. And then it's got a negative relative charge. And then you've got your neutron, relative mass of 1, and a charge of 0. All right. So again, just being able to look at that table, kind of remembering that information. Hopefully everything we've looked at in this video is reviewed to you guys. If you have any questions, please feel free to bring them up during class. And if not, I look forward to seeing you guys again real soon. Take care.